But if we take notes, I don't know. I don't know.
I can take some.
You start, right? Yeah. So this wait for Stefan to take this. Are you recording? Yes.
Let's see if they have enough space.
Okay.
We have nice orange books for notes.
Okay, people. Good morning. So we will start with the technical part. The presentation. The first one will be the Wp3, as you know, climate degradation factors. We are 4 people, but collaborating with in the project. So for starting, we'll have a short introduction, and then we will go through those already 2 years and a half of work, collecting data, available data sources, and then how we apply the climate classification, and then more in details for some 2 climate variables, UV radiance and humidity, then a short summary and overview of our work. So introduction, we have the atmosphere. We will install 1 solar panel, and we want to identify different climate variables for it. We have the sun position, and then we continue with the sun, getting the direct irradiance, incident the modules. Then due to the cloud and the reflection, the albedo, we'll have other components of the irradiance going to the module. The atmosphere, it will have a different component in different locations. Because of this factor, we will have several other variables: precipitation, temperature, wind speed, soiling, and some local shadings and spectral losses, etc. So from all this bunch of variables, we have some of them to study the performance of PV modules, and others to study the degradation of the PV modules. Regarding degradation, we have a new module we'll install outside. We'll get some degradation mechanisms. Our colleagues, they will explain further on this. And we want to reach a certain lifetime in operation. We already identified the climate degradation factors, and we will be talking about those during this today and tomorrow. So UV, humidity, relative wind speed also will be a factor, and then the cycling, the temperature cycling, and all of those individually or combined, they will produce some degradation mode, discoloration, delamination, corrosion, etc. and etc. We divide in indoor testing. So we have some testing PID, water ingress inside the module, and also some climate outdoor, so what will happen outside. We need data to identify those, to start the study. So the locations concerning solar type project, we cover Europe quite okay. The important thing is the people, the experience. So we have representatives from Greece, a second one from Greece, and then we go France, Germany, Slovenia, Italy, the second Italian, and 1/2 Italian, Austria. We cover Europe quite okay. And that is important because we have the feeling of different climate, different variables from different people. If we see to the world as well, from different locations, we have not 1 Mexican, but 2 Mexicans. Then from Africa, we also cover, we have different locations, and that is also really important because if we are talking about the desert in, in Sahara, we go to our friends and we say, hey, how do you feel in summer there? Or, how's your experience? So that is really important, and solar train, we cover a little bit everywhere. But if we go to numbers, here we are now, the line of timeline. We can find some data available online already. We have some site from Solar Train, also the partners or open source databases to cover up 20 years from the past, more or less, some specific locations, the ground stations. But also, several climate institutions, they are working, developing the satellite-based data set, but also climate reanalysis. We'll go in details later on. And also, well, climate projections towards 1100, and so on. Regarding numbers, again, we have the solar trend site in the world, then humidity sensors, we will discuss later also, Stefan, presenting where we installed several devices around the world. The BSRN dataset also provide a lot of information in terms of irradiation and temperature, many locations. Then we have some literature and other sources all around the world. The compendium of degradation rate covering everywhere. And all of these give us a lot of data set to study. We will see how far we are. And even more, we have some specific data sources with Sasha and Wp3, Task 13, and also BIWA is providing some data to the consortium. About ground stations, this is one example of the BSRN station, how they look all around the world, so open field, different surface, and they install a lot of different sensors. All this data is free available online for research. They provide long-time series, high quality, and more things. Regarding the climate reanalysis dataset, we will discuss a lot in those today actually in different work package. So the climate reanalysis, it's a bunch of different data sets from different sources where they will mix from all of those different instruments. Every 6 hours they will model the climate all around the world. And they do, well, they have the data, they have their own climate, and they mix them. So we have the data, we have the model, the climate model, and they call it data simulation to study the climate from the past, the present, and also the future. That is it. And this is like, it looks like hourly data in resolution up to 9 kilometers nowadays. So it's quite precise. We will see the accuracy later also. Wind speed providing, ambient temperature. We have some modeling. So they don't provide relative humidity, for example, but we are modeling it. Then UV radiation also, we model every hour in all the locations. So this one, for example, is quite related with work package 5 and work package 6. Regarding satellite data, we are starting exploring this new data set, for example, and we have this one, the Aura Omni from NASA, ozone monitoring instrument. They are monitoring the ozone and the atmosphere, well, troposphere and all the different, the air up to the space, where they measure the ozone, but also they can do it spectrally to get the UV. We have some comparisons with our data in Ljubljana, and we can see how the satellite data could fit at noon every day, passing 14 times per day around the globe, measuring those. We could use this data. So this one is a further work with work package 5. Luis he will comment more about and how these chemical reactions could affect the polymers, and this is for further studies. And the final one, the climate projection. So we have this a picture. The ozone, for example, they are modeling how the ozone will change if we follow the Montreal Protocol. This is the limitation of the ozone and different chemicals in the atmosphere. And we can see, we can project, estimate on the future. So we have for ozone, and we have also for different climate variables, what will happen in different scenarios. For example, they mostly, the RCP or SSP, they are based on estimations of population, the GDP, urbanization, and all of those factors. They will give you some climate variables changing or projecting along the time. So for example, the radiative force in the irradiance will increase, and also the temperature in different scenarios. And we will see how this will be linked to PV performance and further PV degradation in the next work package. For a summary of this, so we see the climate community, they are really willing to share data with everyone. And that is what we expect from the PV community to follow in this one. It's quite tricky, but we have some experience already. And yeah, they are sharing and they are trying to connect different models. And since a long time, they want to understand the atmosphere, and they are seeing now the climate change and everything, what is happening. So how we can use it? So climate data is free available for research. Historical time series, the BSRN, they provide 20, 30 years of data in hourly or half an hour resolution. Then the climate reanalysis is getting more accurate. This globe, the climate data globally, I presented before. We will see the validation of those for our variables, the most relevant for us. Then the satellite imaging, they are really increasing the accuracy as well. They are going to measure UV now, be raised in different spectra, and so on. And also these climate projections or climate scenarios can help to identify future risk. And yeah, that is about the data set. And if we go now to application of those, we will discuss a little bit how to identify main climate zones around the world. And we have the first one, the Köppen Geiger photovoltaic. It started in 2017, the first beginners week, I think. We identified Köppen Geiger was widely used in the PV community, but we have some discrepancies. For example, the north of Spain is not the same than the UK, and so on and so on. We wanted to improve it, mixing with different variables, creating new climate zones. And for that, well, we took the basic Köppen Geiger, mixing temperature and precipitation. Then we include the irradiation also in the map to create a new climate zones. And further on, the mix of UV, relative humidity into the model, or the classification. This will be also linked, Work Package 4, Work Package 6. This is the published Köppen Geiger photovoltaic, where we mix temperature and precipitation, but also irradiation on the map, creating 12 main climate zones with 2 different characters. And we will see how this could be used for the PV community as well. The first model was in a resolution at 0505 latitude longitude, but now the further research allows us to go to 0101, more detailed map. Now Amantin, well, we continue.
Thank you, Julián. So, we heard a lot about data and the accumulation of them and the classification and how this data can be useful to us. So, as you may have already know, this is the climates that I have been studying for the last 2 years, the 4 usual ones that we have in Fraunhofer, Gran Canaria, Zugspitze, and EDF and Freiburg, and lately we have had some data input also from Luis, and thank you for that. And it has been really interesting just seeing the data to understand that we are not there are dark spots that we cannot see always. So, if I can go on. So, what we have done so far on this aspect, for example, we have analyzed the climates in a very rough way, I would say, just to see how they would fit to each other, or how close they are to each other, how close the distributions are to each other. And the next step that I have tried to do is to make this climate classification based on the thresholds, where we basically decide specific threshold for the UV or the relative humidity and the temperature, and we try to classify. So for example, out of a whole data set, we have plotted here ambient temperature and UV, and we see here the distribution of the data. These are for Leoben. And the idea is to try and simulate the hours that the module passes in this zone, like high humidity, high temperature, high UV, high temperature, very high stress conditions. So what that means is that when the module is found in this area, the factor of the degradation should be higher than when it is in these milder conditions. However, these thresholds so far are set just arbitrarily, and when we put here ambient temperature, it doesn't still make any sense. So the next steps would be to have graphs with module temperatures, which will make more sense to the analysis closer to degradation. And another ongoing process is working on the model comparisons between, there are 3 models that calculate the module temperature. That's all. And we try to see which one would fit best in what climate. Okay. So we have these climates. What I have been dealing lately is the fraction of UV over the whole global irradiation. Out of the whole irradiation that we receive, what amount of it is consisted of UV? And we see here we have some data, okay, numbers. We can see here a rough estimation of what is going on. Here we can see the averages of these 4 climates. But they don't really say anything yet. Like we have different averages which are not really represented on the total UV dosage, which is mostly what interests us. What we can see, though, is that we have, I would say, an early connection points between the tilts of the modules, the latitude also, because they are also connected, and the portion of the UV over the total global irradiation. But this needs still some more analysis. This is just numbers so far. We're still trying to figure out how can this be useful. So when I was here last year, I had this box which I left outside with beers, and here you can see the normal color, the red one, and here it's 1 month of UV plus other radiations like the visible irradiance, but here I have put UV just to make a point. So we have so much data, as also Julián said. So what we want to do is trying to find what are the useful ones. What can we do? How can we take this data and put them into good use? This year I had also the chance to adjust the shadow ring in our facility in Fraunhofer.
We don't install it in the waste bin. So
In the
it's not in the...
yeah. These are different pictures. Okay, so what is this actually? It's a shadow ring where it is used to put shadow here, so we only calculate the diffuse irradiation. So what I was doing was following certain measurements. Will display automatically or? Yeah, okay. So this is basically what I was doing. Just trying to adjust. It's just important to be 0.7. That's what I was saying. But if we can, one day I noticed something. After adjusting the shadow ring, I arrive at this state. I had done my job correctly according to my shade, but I couldn't understand if this was right. And to me, this didn't feel right for a shadow ring to work. So, should I just do my job, or should I do something? So I understood that, yeah, we deal with a lot of data, we analyze so much, but we don't really know where this data is coming from. So it's really important to understand how are these things measured. So, the next slide. Part of my secondment now in Ljubljana is to analyze the different fraction of UV over the total global radiation for different tilts. And for example, we have here some zones with similar tilts, or that there are similar latitudes. And what I saw from Louis' data of the UV, we saw that the numbers were very different from what I've seen in Freiburg and Ljubljana, which was something interesting. Like Do they use different measurement equipment? Do they use different methods? Do they use different units? What is going on? How can we compare and similar stuff? So this is an analysis from the data that we have in Freiburg. We have installed measurement equipment for both at 45 and at horizontal plane. And here we can see a distribution between the whole year. This is for the horizontal plane, the fraction of UV over G, and this is for the 45. As you can see there, this is how the installations are done. However, this graph, it shows something, but we don't really know how to use it yet. And this is the same graph, but for hourly distribution in Freiburg. These are the different distributions of UV over the global irradiation for the different climates. And we also see how much they change. For example, in Gran Canaria, you don't have the same, you have less shift, less different. While in Freiburg, you have a great difference between this ratio. So, in further analysis of this setup, of the irradiance, here I just put a graph just to get like a feeling of how at different latitudes we get different irradiations. So here is at Tripoli, it's at 33, here is, and as we go down, it means that we're moving upwards on the globe. We're having less irradiation. So, what I want to do is to calculate UV over the global irradiation. So on the left you can see a radiometer we have at Fraunhofer, and here you can see a spectrometer that it's installed in Ljubljana. One thing I noticed that I was not aware of was the spectral response of the measurement equipment. But I have always taken it for granted because I was just dealing with data. So on this side we can see the spectral response of the UV radiometer, and this is coming from a different source. It's not from this equipment, but it's because I couldn't understand. Some of them had just this range, 300 to 100 to 1100. But you don't really know, like, does it distribute like that? This is for a solar cell, and this is for a pyranometer. So coming to that question, I guess this is why they use pyranometers, because they are more accurate and they can have a broader sensitivity. So how does this spectral sensitivity affect our readings? This is our normalized sensitivity of the sensor. This is the irradiation, and just by a simple multiplication we get the number that we analyze in the data later of the UV. So, to come back to my experiment, what I did, what I'm currently doing in my secondment in Ljubljana, is I bought some cheap sensors from China, and here I have analyzed, I have put them in a table to have different ranges, and the data sheets were also not so descriptive. Like some of them, they had the response wavelengths. Some of them, they also had their spectral response, which are these graphs. Some of them, they didn't have. They didn't even have a spectral response. So it's really, you don't really know what you measure sometimes. So the idea was to put them all in a row and expose them at the same tilt and try to understand how they respond. So initial, the whole idea is to put them in different tilts, 45, 31, 23, and 0. It's the tilts we also use in our sites. So I made a 3D model, and then with the help of some colleagues in Ljubljana, we 3D printed a module, a plastic thing. And the idea is to install all the sensor on and try to measure. But before we install different sensors, we thought that it's better to install only one kind of sensor, and I was trying to understand which one is the best. Also, this process had a lot of middle steps with the microcontroller, like you had to know the connections, you have to do the code, you have to read the values correctly. So, after some time, I arrive at this concept where I have the 4 different kinds of sensors all together, and I managed to get some data from them. We attempted to measure the sensors to see how much they respond to monochromatic, because when we expose them to monochromatic lasers, let's say green, we know the wavelength, and we can understand how much they are responding to that. But we couldn't do any of that because the sensors were too small. So the second attempt is to be discussed in more the future. So what I did was I was trying to understand if these sensors make any sense at all in the beginning. So I just exposed them to a halogen lamp. They were responding quite logically. And then I exposed them to a UV LED light. They were also responding some way, but the numbers they were giving were weird. So what I wanted to do is to take a spectrometer that I found and the colleagues from Ljubljana shared with me, and I exposed the UV sensors with the spectral response. So what I did, I took a metal rod with some holes in it, I put the optical fiber inside, and I screwed this on top. So this was just to measure for this one. Next, in order to take the spectrometer and my sensors, what I did was I put this on this hole, and the other one I just attached on top of it, on the side. It's not very accurate, but it was good given the circumstances. So I exposed them like that for an hour, and this is the graph I got. It was clear sky day, so I guess the measurement was as accurate as possible. So as you can see, they have different measurements. What are these? For example, in the beginning I just put it in a random tilt, the whole setup. And here you can see some drops. And these drops, what are they? It's when I was taking the sensors and I was putting them on a horizontal one. On the increasing side, they were exposed more at tilt. And at this point where we have the drops here, what I was doing was shading the sensors and the spectrometer. Here you cannot see it in this picture, but I tried to make a more uniform shadow. So these graphs show us that we have some sense, but the numbers are more weird and they need some more analysis. See, like for example, these sensors, they give 1/3. This one 3.44, 771, 1000. Very different scales. So, also in the between all of this process, there are so many microprocesses that you have to go through. For example, that the data is coming that way, and you cannot give it immediately to your computer for analysis, and you have to take another module to send it through Wi-Fi, and then to transfer this data into this format, and then analyze it. So, I had 4 sensors with different spectral, according to data sensitivities, or none at all, and the spectrometer that measures the whole thing. So what I wanted to do is try to understand how good are these related, these measurements related. So I put them on a table. On this side I put the sensors, and on this side I have the different wavelength ranges taken from the spectrometer. And I tried to do some kind of fitting. So here, for example, the sensors were correlated with each other. And here the sensors were correlated according to the wavelength that we had from the spectrometer. So as we can see below the 350 nanometers, the correlation between the sensors and the spectrometer is quite poor. But after the 315, the correlation becomes better for some sensors. However, the problem here was that this sensor was in the data sheet was saying from 320 to 420, and this was from 200 to 370. And we see that in this range, it doesn't really perform better. So anyway, the point was made that we will order only one set of sensors. So I ordered 5 of these sensors, which are yet to come, and to install them on the thing. So currently the project is stuck due to we're waiting for the sensors and so many small bugs and other micro stuff that are not really related to the work, but you have to go through. So this was all for the outdoor UV radiance. Now we're going to see some setups about the indoor UV radiance. Stefan Mitterhofer.
Yes, as you know, one of the goals of Work Package 3 is also to connect the outdoor with indoor. So we want to build indoor setups to also recreate what we see in the outdoor climatic data. And one thing we are building is an indoor light source for UV irradiance. And we do an LED-based light source, and we use water cooling. Some of you might, hey, that's a great idea. Some of you might think that's really stupid, but it's your idea. It's in the project proposal. So, yeah, and I mean, it would actually be a great idea. LEDs are gaining a lot of market share. There's lots of technological improvements in them, and as we all, or most of us probably have seen, there are already flashers based on LEDs. However, there is one big problem. For degradation, UV light is actually the one that causes the most damage, and as we also see here, there aren't really many LEDs available in the deep UV. We also did a short market analysis, and we can see it clearly. Those are all LEDs from one manufacturer of different wavelengths, and the lowest wavelength where one can get quite strong LEDs is around 365. So there has to have to be more technological improvements to get economic and also powerful LEDs below that. This is related to some problems with the semiconductors. And we still wanted to analyze this, so we made a small setup. So we designed some electronics that drove some LEDs. We bought LEDs at 365 and 385 nanometers. And we degraded glass EVA glass samples below this LED light.
You tried to.
We tried to, yes. And we did this for 7,500 hours, and we analyzed now the spectral transmittance of the samples, and at the end we also did Fourier transform infrared spectroscopy and differential scanning calorimetry. And we saw some changes in the transmittance of UV light, so there were some changes in the material, so over time, under the 365 nanometer light, the samples got more and more transmittent. However, the other analysis didn't yield any conclusive results, so there were no chemical changes in the encapsulant itself. And this wasn't very surprising, at least not to the guys who knew something about it. It was surprising to me, because there are aliphatic CC bounds in the material, and the wavelength for them to be broken is at 357 nanometers. So if we are above this wavelength, light just doesn't have the energy to do any serious chemical degradation of the material. So to really do good experiments with LEDs, with degradation experiments, we need more economic, more stable, and more powerful LEDs. However, it's of course also lots of collaboration between Work Package 3 and Work Package 5. However, we still went on to make an LED setup for our climatic chamber, and we wanted to keep it as modular as possible so it could in the future also be updated with new LEDs. And we did, actually a master student at the University of Julián did this, designed some drivers for these LEDs, which then could be controlled in a daisy chain operation, so we could put as many LEDs as we wanted in a chain and then build an array of these LEDs. And we did our own calculations, so if we just put all LEDs and drive them at 100% of the power, we get quite a non-uniform irradiance, so we also have to dim the central LEDs to get a nice and homogeneity of the radiation. And as a base for this, we used an aluminum plate we designed, and we had some channels for water cooling, and all the LEDs were then on the other side. And we also made it modular, so we could stack as many of these aluminum plates together to have larger and larger arrays, and maybe even scale it then up at some point to full-size modules and not only small test modules. And we did then some kind of characterization of the LEDs and then also of the array that we built. We see here one of these measurements, and we got really, really good fit between our calculations and the measurements. However, you might remember this from the last meeting, we had some initial problems, namely that the enclosure wasn't completely closed. So there was water ingress into the array itself, and it completely degraded our array and completely screwed it up. So we had to rebuild all the drivers, which we are currently doing right now. So we got them a few days ago just, and yeah, after we rebuild them, we will remeasure them and we'll then test the degradation of the array in the chamber. So now let's move on to the next thing that we analyzed a bit more indoor, and that is humidity as also one really big factor of degradation of PV modules. And also there we analyzed the outdoors, but also connected it to indoor measurements and also the simulations and calculations that we did. And for the outdoor setup, we did a collaboration with partners inside SolarTrain, but we also managed to get a few outside universities and institutes to collaborate with us. And there we measure moisture ingress in MIDI modules in many different climates. You've seen in the beginning a small map from Julián where we've put these setups. And we built 3 mini modules per setup. And you can see a layout of these modules here. And each of these black dots is one moisture sensor, which measures the temperature and the humidity, the moisture. And we also designed some custom readout electronics, and also it's driven by a Raspberry Pi. The data is then uploaded. And the current status of this experiment is that 4 setups are installed. So we see here the one in Urach, the one in Rome, the one in Ljubljana is inside the climatic chamber, and we do some tests at more controlled conditions. The one in Singapore is also installed, and the one in Chile, in Atacama, it arrived this week, so it will be installed next week there. And so the current work is to keep it going and to analyze the data. And for the data analysis, it's actually nothing really special, so we do some data filtering. You see here also some preliminary results. We see actually that Rome and Bolzano are very similar from the results. Singapore is much more constant. For one, the day-night cycle is not as extreme there because it's much more cloudy, so the module temperature usually doesn't get as high during the day, but also generally the weather, so there's much less seasonality there. But we also see quite a nice result, so the 3 sensors that we have beside the cell, not in front of the cell, they really follow daily and weekly trends. So if there's a week of rain, you really see that in the moisture at this point in the module also. And here we see some more smoothed out data to get the temperature coefficient out of the humidity measurements. And this, for example, is the data for Singapore for one module. So this is, as I already said, for these 3 sensors beside the cell, you really see the weekly and daily variations still quite well. However, we also wanted to measure this indoor and also to model it, to calculate it. And this is, of course, also again a collaboration with Work Package 5. And for this setup, we also use the miniature sensor, this method which was developed by Jankovic. And we are currently measuring 4 encapsulant inside the climatic chamber, then 5 back sheets, all with EVA together. And here we can see how one of these samples looks like. This is just one sample with an encapsulant. So we have 3 sensors inside the encapsulant and 1 outside that measures the air close to the sample. And for the chamber settings, this is just the overall thing. So we already did these measurements, and everything that's below still has to come. So we do different temperatures to also get the temperature coefficient of the different materials out. And how do we want to connect now the indoors with the outdoors? For this, we use some calculations and we do some modeling. And usually this is done with the Fiction model, which is really standard, really very widely used model, and it's the nice thing, it's really simple. So there's just one material parameter that describes how fast moisture gets through. And we did some simulations based on that, and we saw that, I mean, for some materials, for example, for the EVA, it's actually quite a nice, it actually gets even a bit better at higher temperatures then, but for other materials, it's actually quite far off. So we tried to develop our own model. The first iteration we see here, it was based on a heterogeneous mesh that tries to simulate two different interacting mechanisms. Yeah, we implemented this in finite element simulations, and we got actually much nicer and much more accurate results for our measurements. However, it has one really big problem. There are many interfaces between materials, and it needs a very fine mesh in the simulations to simulate this accurately. What that means is basically the simulations just take a very long time, and we have to wait a long time for the results. Especially to optimize the parameters, this can be a problem, and also to extend this into full-sized modules, it's not really good. So we went on to try to make an analytical model. So here we get a little bit deeper into the physics, and sorry for that. So the common approach to implement two different types of sorption in materials is that we have one normal type of sorption, which is normal Fiction diffusion, and there is also a second type of sorption, which is usually called Langmuir type sorption. And this name comes actually from how gas molecules go onto the surface of go onto any surface. It has also been used for gas diffusion through polymers, and it was 1978 the first time also used for moisture diffusion through polymers. So these are the two types of diffusion. However, there is one problem with this theory, namely that there is only one single layer possible. So there are certain states, there are certain positions in the material where water can get on, but then this position is full and nothing else can happen. And so we looked to other theories for gas sorption surfaces, and there is one extension to this theory, it's called Wp3 sorption, that basically takes the exactly same, but it goes to multi-layer absorption. And we want to do the same with moisture diffusion. And to describe this, we made, I mean, this is just how it's mathematically described. It's a system of n differential equations. And the sensor would measure, in this case, only the C1, which is the mobile part, which is the part that can diffuse through the material and can reach at some point the sensor. Looks complicated, but it's actually quite nice, and it's only 3 material parameters, so that's the absolute minimum that we have with 2 different types of sorption. And now the question is, can there be some mathematical simplification? Does it have to be so many differential equations? We didn't find one yet, but we found something we can do. And we derived this simplification analytically by describing analytically our model that was based on the heterogeneous mesh. And yeah, this is basically the result. So we see we don't have any nonlinear terms anymore in the concentration. Still 3 material parameters. And so a really quick overview of the 3 models. So the old model, the Fiction model, of course, it's much simpler. It has just one parameter. It goes really fast, and it's also very mature. It has been used for a long time, and people are used to using that model. However, as we've seen, the accuracy was not that good. For the absorption models with 2 different mechanisms, the one based on the mesh is also quite simple. So there we don't change anything on the mathematics, and it's very accurate, but it takes a lot of time. And the analytical model, it's sadly much more complicated, but it's as accurate as the other one, and it also goes much faster. So now, as concluding remarks of work package 3, you see here what all the deliverables were and the milestones. We submitted most of them in time, or with very short delays only, and there's still one work ongoing for the last deliverable, which will be due next year. And here, just a short overview over the time of different things we did. First for the indoor, like in 2017-18, we started with the radiance optimization, started to do the calculations for the array. Then in 2018-2019, also started our moisture ingress, and we also did some PID tests, and the results will then be also in log package 4 later. And the current work and ongoing work is then, again, work with UV outdoors. Some outdoor data from PID is still ongoing, but Aziz will present really short a bit later. And of course we do more moisture modeling, and I mean this is the exact same for the outdoors. So again, the time frame of what we did till now. In the beginning, it was mostly looking at the correlations of different outdoor climatic parameters. We also defined which parameters are really critical for the degradation of PV modules and for their performance. Then later on, it went to the classifications. It went to more in-depth analysis of the data sets and of the correlations. And yeah, now ongoing work is still further the classifications, the threshold values, the extended Köppen Geiger PV, and so on. And yeah, so that was what. So, any questions, especially for those guys?
I already understood that.